The Iron Heart. 75 years of history in the manufacturing of an ammonia compressor crankshaft. The metallic sound resonates through stained concrete walls. Pneumatic hammers strike steel with rhythmic violence, while open furnaces spit orange flames that illuminate faces covered in soot and sweat. This is the setting where one of the most fundamental pieces of modern industry is born, the crankshaft of an ammonia compressor. For more than 7 decades, this robust gear has been the beating heart of industrial refrigeration systems, cold storage facilities, chemical plants, and transport ships that cross oceans carrying frozen food to the entire world. But the history of this piece of surgical precision goes far beyond technical drawings and engineering specifications. It is a narrative woven with fire, molten metal, human sacrifice, and a tradition that spans generations of anonymous workers. Since the 1950s, when ammonia compression systems began to expand globally as the dominant solution for large-scale industrial refrigeration, the crankshaft established itself as a critical and irreplaceable component. Unlike other parts that can be mass-produced with relative simplicity, the crankshaft requires a unique combination of structural strength, microscopic dimensional precision, and the ability to withstand millions of rotation cycles under colossal pressures and extreme temperatures. Each crankshaft is designed to convert the linear movement of pistons into continuous rotation, distributing forces that can reach hundreds of tons through its carefully balanced structure. A single defect, an imperceptible crack, an imbalance of a few grams, and the entire machine can collapse catastrophically, causing millions of dollars in losses and putting lives at risk. Manufacturing begins with meticulous selection of raw materials. Any common steel won't do. The chosen material must be a special alloy, generally based on chromium molybdenum steel or high-strength carbon steel, capable of withstanding cyclic loads without suffering premature fatigue. These metal blocks arrive at factories in raw state, weighing hundreds of kilograms, still without defined shape. The first stage of transformation occurs in forging furnaces, where steel is heated until reaching temperatures between 1100 and 1250 degrees Celsius, becoming incandescent, malleable, almost liquid at its core. In this critical state, the metal is removed from the furnace with giant tongs operated by men who must coordinate their movements with military precision, as any hesitation can result in severe burns or fatal accidents. The burning block is then positioned under hydraulic presses or forging hammers that can exert forces of up to 5,000 tons. Each blow resonates like metallic thunder, making the floor shake and the air vibrate. Dozens, sometimes hundreds of controlled impacts are necessary to gradually mold the raw metal into the basic shape of the crankshaft. The process requires not only brute force from the machines, but also the experience of operators, who visually assess the color of the metal, the surface texture, and the sound produced by the blows to determine the exact moment to reposition the piece or return it to the furnace for reheating. This is an art transmitted from master to apprentice, knowledge that is not found in technical manuals, but in calloused hands and intuition developed over decades of work. After initial forging, the crankshaft undergoes a series of complex heat treatments. It is heated again, this time in a more controlled manner, and then cooled at specific rates to induce changes in the crystalline structure of the steel. These tempering and annealing processes determine the final properties of the piece: surface hardness to resist wear, core toughness to absorb impacts, and resilience to withstand constant vibrations. An error at these stages can irreparably compromise the piece, making it too brittle or excessively soft. It is at this point that metallurgical science meets the practical experience of technicians, who adjust furnaces and control treatment atmospheres with almost alchemical precision. Then comes the machining stage, where the raw crankshaft is transformed into a work of precision. Specialized machine tools, equipped with milling machines, lathes, and grinders, remove layers of metal with tolerances measured in thousandths of a millimeter. The bearings, surfaces where the crankshaft rests on the roller bearings, need to have mirror finishes and exact dimensions, as any imperfection will generate excessive friction, heat, and accelerated wear. The counterweights need to be positioned mathematically to ensure perfect dynamic balance, avoiding vibrations that could destroy the entire compressor. Specialized operators program modern CNC machines or, in more traditional workshops, manually manipulate lathes and milling machines with almost artistic skill, feeling through the tools each resistance of the metal, each variation in surface texture. Final balancing is a critical process performed on high-precision machines that spin the crankshaft at high speeds while sensors detect any irregularity in mass distribution. Small amounts of metal are strategically removed from the counterweights until the piece rotates perfectly balanced, without causing measurable vibration. It is meticulous work that can take hours and requires infinite patience, as the final result will determine not only the compressor's efficiency, but also its durability and operational reliability for decades of continuous use. But while in modern factories in Germany, Japan, and the United States this process is largely automated, with robots handling incandescent parts, sensors monitoring each stage, and industrial ventilation systems removing toxic fumes, the reality in much of the developing world tells a radically different story. In industrial cities of Pakistan like Lahore, Gujranwala, and Karachi, in factory districts of India like Faridabad, Ludhiana, and Rajkot, and in industrial zones of Bangladesh, working conditions seem frozen in time, replicating environments that were abandoned decades ago in the developed world. In these improvised workshops, frequently installed in precarious sheds with zinc roofs that transform the environment into furnaces under the relentless sun of the Asian subcontinent, men work in conditions that defy any basic notion of safety or human dignity. The ambient heat already easily exceeds 45 degrees Celsius during summer months, and when you add the radiant heat from open furnaces, incandescent metals, and welding operations, perceived temperatures can reach 60 or even 70 degrees. There are no air conditioning systems, adequate fans rarely exist, and natural ventilation is minimal. Workers sweat profusely, losing liters of fluid that must be constantly replaced under risk of severe dehydration and heat collapse. Individual protection is practically non-existent or drastically inadequate. While international standards require heat-resistant clothing, specialized thermal gloves, protective eyewear with appropriate filters, respiratory masks with filters for metallic particles and toxic gases, hearing protection against noise that frequently exceeds 100 decibels, and safety boots with steel toes and thermal insulating soles, what is seen in these workshops are men working in common clothes already torn and soaked with sweat, many barefoot or wearing simple sandals without any eye protection while operating grinders that launch incandescent sparks in all directions, without masks while breathing air saturated with smoke from burned oil, metallic vapors, and fine particles of iron and other heavy metals. The impact on these workers' health is devastating and cumulative. Epidemiological studies conducted in industrial communities of these regions document alarming rates of chronic respiratory diseases, including pneumoconiosis, lung disease caused by inhalation of mineral dust, chronic bronchitis, pulmonary emphysema, and occupational asthma. Prolonged exposure to burned oil vapors and incomplete combustion products is associated with elevated rates of lung cancer and other respiratory neoplasms. Hearing loss is practically universal among workers with more than a decade of experience, result of daily exposure to noise levels that progressively destroy the hair cells of the inner ear. Burns are so common that many workers exhibit extensive scars on arms, hands, and face, permanent marks of decades handling metals at temperatures that can carbonize human skin instantly. There is also the issue of non-existent ergonomics. Large crankshafts can weigh hundreds of kilograms, and their handling frequently requires brutal physical force. Workers lift, carry, and position these heavy pieces repeatedly throughout shifts that can extend for 12 or even 16 hours daily, 6 or 7 days a week. The result is an epidemic of musculoskeletal injuries, including herniated discs, chronic joint damage, early arthritis, and repetitive strain injuries that leave still young men permanently disabled. It is not uncommon to find workers in their 40s with the mobility and physical capacity of people 20 or 30 years older. The presence of child labor adds an even darker layer to this reality. In some smaller workshops, especially those operating in the informal economy without registration or government oversight, adolescents and even children can be found performing dangerous tasks. They operate grinders, carry heavy pieces, feed furnaces, and learn the trade under the same dangerous conditions as adults. The justification is always the same: extreme economic necessity, family tradition, lack of educational or employment alternatives. But the price paid is irreversible: young bodies subjected to stresses for which they are not prepared, interrupted education, stolen childhoods, and futures compromised by permanent physical sequelae. Despite all this hardship, there is a deep and genuine pride in these workshops. Workers know that their hands, literally, shape essential components for global industrial infrastructure. They know that the crankshafts they produce will be installed in compressors that refrigerate food in European supermarkets, that keep vaccines chilled in North American hospitals, that enable the operation of petrochemical plants in East Asia. There is an awareness that their work, however invisible and unrecognized it may be, sustains critical systems on which billions of people indirectly depend. This professional consciousness, transmitted from generation to generation, creates a culture of craftsmanship where work quality is a matter of personal honor, even when conditions are brutal and external recognition is non-existent. Master craftsmen, men with decades of experience whose skills are irreplaceable, develop an almost intimate relationship with the metal. They can assess the quality of steel by the color it assumes when heated, by the sound it produces when struck, by the resistance it offers to cutting tools. They can detect defects invisible to the untrained eye, prevent cracks before they form, compensate for imperfections in raw material through subtle adjustments in the process. This tacit knowledge, accumulated through years of trial and error, careful observation, and direct learning from even more experienced masters, cannot be easily codified in manuals or replicated by machines. It is a technical cultural heritage that exists only in the minds and hands of these workers. The global economic chain that connects these workshops to industries in the developed world is complex and often deliberately opaque. Companies from wealthy countries outsource component manufacturing to suppliers in South Asia, who in turn subcontract parts of the work to smaller workshops, creating multiple layers of intermediaries. Each layer extracts its profit margin, and the end result is that the workers who actually manufacture the parts receive only a minimal fraction of the product's final value. A crankshaft that can cost thousands of dollars when installed in a new compressor in the European market may have generated only a few dozen dollars in wages for the workers who forged, machined, and balanced it. This economic asymmetry is maintained by the lack of effective union organization, the abundance of labor desperate for any type of employment, and companies' ability to simply move production to other regions if labor costs begin to increase. In recent years, pressures from conscious consumers and stricter regulations in some developed countries have forced multinational companies to implement audits of their supply chains, verifying working conditions in outsourced suppliers. But these audits are frequently announced in advance, allowing workshops to temporarily improve conditions, hide underage workers, and present fabricated documentation. As soon as auditors leave, everything returns to normal. Furthermore, the constant pressure for increasingly lower prices created by global competition means that significant improvements in working conditions, which would inevitably increase costs, can make a supplier uncompetitive, leading to loss of contracts and closure of operations. Contrasting strongly with this reality, modern factories in developed countries present a radically different scenario. In industrial plants in Germany, Sweden, Japan, and the United States, crankshaft manufacturing is largely automated and robotized. Workers operate control panels in temperature-controlled rooms, monitoring screens displaying real-time data from dozens of sensors. Robots handle incandescent parts with millimetric precision, immune to heat and fatigue. Industrial ventilation systems capture fumes and particles before they can be inhaled. Personal protective equipment is mandatory and rigorously enforced, with severe penalties for companies that do not comply with safety standards. Work shifts are regulated, breaks are mandatory, and robust health benefits ensure that workers have access to preventive medical care and immediate treatment of any occupational injury or illness. But even in these advanced factories, challenges remain. Constant pressure for greater productivity, the introduction of new technologies that make traditional skills obsolete, and the ever-present threat that production will be transferred to regions with lower costs create anxiety and insecurity. Skilled workers find themselves having to constantly update their skills, learn to program increasingly complex CNC machines, master three-dimensional modeling software and finite element analysis. The nature of industrial work is changing rapidly, and those who cannot keep up face premature professional obsolescence. Crankshaft manufacturing technology has also evolved dramatically in recent decades. Modern processes include isothermal forging, where temperature and pressure are controlled with extreme precision to produce ideal metallurgical structures, high-speed machining with ceramic and polycrystalline diamond tools that allow previously unimaginable tolerances, advanced surface treatments like plasma nitriding, which hardens only the outer layers while maintaining a tough core, and non-destructive inspection techniques using ultrasound, magnetic particles and X-rays that can detect microscopic internal defects invisible externally. These advances allow the manufacturing of increasingly lighter, stronger, and more durable crankshafts, capable of operating at higher speeds and with greater energy efficiency. Simultaneously, there is growth in alternative technologies that may eventually reduce or even eliminate the need for traditional crankshafts in some applications. Scroll compressors, screw compressors, and magnetic compression technologies are gradually gaining market share, especially in smaller-scale applications. But for large-scale industrial systems, where absolute reliability and maintainability are paramount, the traditional reciprocating compressor with conventional crankshaft still reigns supreme. The reason is simple. After 7 decades of development and millions of hours of field operation, the design principles, materials, and manufacturing processes have been refined to a point where failure rates are extraordinarily low and operational behavior is completely predictable. The lifespan of a well-manufactured and properly maintained crankshaft can extend for decades, easily exceeding 30 or 40 years of continuous operation. During this period, it will complete hundreds of millions, even billions of rotations, withstanding cyclic loads that would test the limits of any material. Occasional repairs are possible through specialized welding techniques and remachining, allowing worn bearings to be recovered and the piece returned to almost original specifications. This extraordinary durability represents not only superior engineering, but also a tribute to the quality of human work invested in its manufacturing. When finally a crankshaft reaches the end of its useful life, it is frequently not discarded but recycled. The high-quality steel is melted again, becoming raw material for new parts, closing a cycle that can repeat indefinitely. In this sense, each crankshaft carries not only the history of its own manufacturing, but also material fragments of previous generations of components, metal atoms that have already passed through multiple industrial lives, each contributing to the functioning of human civilization. This story of 75 years of crankshaft manufacturing for ammonia compressors is, at bottom, a story about the dual nature of human progress. On one hand, it represents extraordinary triumphs of engineering, metallurgy, materials science, and precision manufacturing. It demonstrates our capacity to master complex physical processes, to transform raw matter into sophisticated tools that dramatically expand our collective capabilities. On the other hand, it reveals the deep inequalities and injustices that still permeate the global economic system, where the same product can be manufactured under radically different conditions depending only on where on the planet the work occurs. It is impossible to look at a gleaming crankshaft perfectly balanced and ready for installation, without thinking of the hands that shaped it, the lungs that inhaled toxic fumes during its manufacturing, the backs that bore its weight, the ears that were deafened by the roar of machines. Each piece carries invisible but indelibly the marks of human sacrifice, of knowledge transmitted through generations, of professional pride that persists even under the most adverse conditions. This is the true iron heart, not just the forged metal, but the human will that continues beating inside each workshop, each factory, each shed where men and women transform raw elements into machines.